Welcome to Gabversity, where facts care not about your feelings. And the brightness is now all the way up so I can see what's going on. And it is a pleasure to see everybody. We have Nellie Bell, we have the whole family. So this is going to be some heavy calculus, and the calculus is going to show mathematically, right, the possibility of finding a particle outside the classically allowed region. And this is very interesting, Captain Deltron, the team. Why? Where was the comedy? Hey, Cyanide, long time no see. I hope you are doing well and killing it with your awesome fan base and your great variety of entertainment and deep and meaningfuls. Lovely to see you all. All right, so we're going to find the location of the particle, hello, outside of the classically allowed regions. And this is weird, right? Because remember, if you throw a ball, right, you expect the ball, if you throw the ball off the cliff, right, you're going to see the ball land in a certain location. If you keep throwing the ball off the cliff, it's going to land in certain locations. But the chance that it lands like in Antarctica, like on the other side of the world, that wouldn't happen. But in quantum mechanics, something like that can happen. And it's really interesting. So I'm going to draw it for you, and then we'll show you. All right? Alrighty, so here we go. Remember the cliff, and we had sort of God's Dead or Cyanide or whoever it was, everyone here, right, throwing something off the cliff. You ready? Here we go. We're going to throw the rock. Hey, Tommy Watkins. Welcome back, my friend. You have an awesome day or evening wherever you are with your lovely man. Hey, Cyanide. All right, so imagine now Cyanide throws one, right? I don't have my magnifying glass. That was an explosive rock. It was. It was. All right. So now what we're going to do is now God's Dead's going to throw something. So God's Dead's over here, okay? And God's Dead goes, right? And then someone else and someone else, someone else. And you end up getting this location of roughly where all the rocks land and explode. You keep throwing stuff off the cliff, homie. What is it with you? All right. So you get an average, but in quantum mechanics, sometimes you'll throw it and it'll end up over here, like for no reason, way over there, Acme Rocks, or over here, right? Or over there. What the hell's that about, right? And so we're going to do the mathematics to show you what actually goes on. So here, remember, with a harmonic oscillator ground state, right, we have the wave function, and this is the wave function, right? No time involved. This is a snapshot, right? A snapshot only, which is mass by omega, which is the spin, superposition, yes, you know your stuff, over pi, which is the number, h, which is the pixels of the universe, h bar. All right, so this is just the equation, right? And then we have e to the minus m omega x squared over 2h bar. All right, all that is the equation for that, right, of x. Okay, that's the ground state. So you guys are throwing rocks off the cliff, right? You're just throwing them normally. You haven't had Red Bull. You haven't come back from a party, because if you were, then you'd be really excited and throw the rocks even further, right? So that's not what we're doing. What we're doing is you're just having a decent day and just throwing them off the cliff, right? So you expect them to land in a certain location, and the location is defined by the equation that I just wrote. All right? So here we go. Here it is again. Now the probability, right? The probability of finding it. So here are the rocks. Let's call this side A and this side B. Okay? So that is where you would find the rocks. Okay? You would expect to find the rocks between A and B. You wouldn't want to find them over here or right outside B. That would be weird, right? So what we're doing is to show that the probability of finding it between A and B, probability of finding between A and B. So the probability of finding it in here, right? Now with classical physics, classical mechanics, you would expect the probability to be 100%, right? Because if you're throwing rocks, you would expect that the average location is going to be in that location, right? You wouldn't expect it to be on the other side of the world. That would be weird. Okay, so, but here's something interesting. It's actually, please find my rocks. All right, it would be the integral, okay, from A to B, right, that, which is the wave function, squared, okay, x, dx. All right, so all that is, it's 0, right? Because you guys are throwing the rocks and you haven't had Red Bull. If you had Red Bull, then the wave function would be wave 1 or wave 2 or wave 3, because you have heaps of energy. But at the moment, you're just regular throwing the rocks. So the probability of finding those rocks in the location should be 1. Acme heat seeking, yeah. That'd be good. We could use them over in ISIS land. So the probability of finding it should be 1. 1 means 100%. It means you're always going to find it. But that's not what happens. A weird thing happens, right? The weird thing is that it's not 100%. What's that about? All right. So here we go. I'm going to expand this. Okay. So does Pythagoras equation apply? It does, but in a this is a calculus version. But you could use it actually if you wanted to. Let me eat you. Oh, look at that! You have some women after you too. That's pretty hot. I'm sorry for the cyanide. Sit on my face. Wow, there you go. You've got some interesting fans there, cyanide. All right. So now let's do the probability classical. All right. All right. The classical probability, right? What you do is you would just put the integral of minus the square root of, speaking of square roots, 2 times the energy over m omega squared. Okay, that's negative. Yes, talk about it. Here is the energy, right? And that would be this side, let's just say. Okay, that here, you could call that mathematically, you would call it minus 2 by the energy over mass by omega, which is the spin squared, right? So that would be the minus, and this would be on this side would be the plus. So that would be plus 2 times the energy over mass by omega squared, right? So you'd expect to find the part of the rocks between here and here, and that would be classical physics. So up here you put the plus, which is plus square root of 2 energy over mass omega squared, right? So between the minus side and the plus side, right? Obviously this is 3 dimensions, but we're only doing 1-dimensional maths. We're assuming the rocks all land in a line, which would never happen in real life, but we're keeping it simple. All right, of the wave function squared dx. Alrighty, so that here would be the classical, and that's the wave function, right? Now what actually happens is, let's have a look at what the answer is, and that's for classical physics. There you go. The classical answer, right? The classical answer is that you should get, right, approximately 84%. Hey, Soul King is back. You should get about 84% chance. So what they're saying, what would be the equation for a 3D solution? Ooh, good question. We are going to get there. In the next couple of weeks, we're going to upgrade our maths to 3D level. And then plus time, it'll be 4D. So get ready, because in a few weeks, we are going to do 4-dimensional mathematics. Yeah, it's going to be 4-dimensional, my friend, which is even more awesome. What is the integral? The integral is 84%. It's going to be fun. Yeah, damn straight. 4-dimensional maths is awesome. It's awesome. Blows your mind, because it makes you realize that time is not linear. It makes you, hey, ¿cómo está acá? It makes you realize that time is a location in 4-dimensional space, and our consciousness rides those waves. Yeah, 4D with time. It's absolutely amazing that, yeah, it's really, really interesting. All right, so basically with classical mechanics, we've discovered that if Zero Art, Homie, McDuda, oh shit, and Cyanide, if you guys threw rocks, there's an 84% chance that it's going to land in that center location, right? Without Red Bull. Okay, so there's an 84% chance it's going to land here now, because some might land here, some might land here. Hey, no Tifa. All right, have a look at this, right? The chance with quantum mechanics, right? This is, where am I here? All right, hold on a sec. Now here's an interesting thing. I actually went too fast. I'm sorry. I went too fast and I skipped. I keep changing the equation. All right, so I said to you at the beginning that there's a 100% chance it's going to fall in that location for classical physics. Okay, there's a 100% chance that it's going to fall in the location for classical physics. But for quantum mechanics, something weird happens. Something weird is that it doesn't always land. My brain is a comet. Yeah, it orbits in a very bad fashion, sometimes crashes into planets. That's my brain. All right. Alrighty. Yes, that is a... Hey. Alright, so here is cyanide, here is homie, here and McDuda. We're going to put McDuda in, McDuda, Udaye. We got Notifa, and you're all throwing rocks. Right? Where does the rock land in 4D? Ooh, that's interesting. In 4 dimensions, the rock never lands. You have to travel to that location to see the rock. Alright, he's in. Okay, so here we go. All of them land in this area. None of them land over here or here, right? But in quantum mechanics, for some reason, sometimes the rock will land here and here for no reason. And so classic equals 100%, okay? But in P quantum, it actually is only 84%. So that is very interesting because mathematically it uses something called the error function. And I'm going to show you the error function. Okay. This is really interesting, right? This function mathematically, right? Now in physics they give you the answer, but in mathematics we describe the error function as something that doesn't fit in this universe, but it pops up in mathematics. It's absolutely amazing, right? So there is a number that we can't even write. Error or error. Oh, sorry. Yes, good question. Error. E-R-R-O-R. It's called ERF. In mathematics, we write it as the ERF, right? And it is a number that we can't even write. No one even knows how to write this number. Yeah, right? It's this weird-ass number. I'm so happy to find... Awesome, Samantha. That is awesome. And you should be around 33 years old, which is the error function. That's right. And I'm going to show you what it looks like, right? And this is so cool because this number... It's an alien number, and mathematicians have been working on it for years to try and figure out what this number is, but no one can find it yet. This number, right, you would think it makes no sense, but it turns out that that weird number that no one can calculate is exactly what happens in quantum mechanics, right? It is why the rock doesn't end up 100% of the time where you think it's going to go. Sometimes, like, you know, you guys, McDuda might throw the rock, Sinai throws the rock, and instead of landing underneath the cliff, one of them lands in the Middle East, right, on the other side of the world, for no reason that humans can figure out, right? Sometimes it'll land on the other side of the wall, right? If you have a wall around where you're throwing the rocks, it goes right through the wall. So even the Trump wall couldn't stop it. That'd be your rock. What's this called? This is quantum mechanics. And I'll show you the number, right? So here is, the number can only be expressed as an infinite sum of another number. Here it is, right? So this is the, here is the number. So first of all, here is a function. This is called e to the x squared. Okay. Now this number is just it's a function, right? So this function sort of looks like this. It sort of looks like, let's say e to the 0 will be 1. So when x is 0, it's going to be 1. When x is 2, that's going to be e to the 2 squared is e to the 4, so it's going to be up here. And minus, it's also going to be up here. Okay, so, alright. So this is sort of what the function looks like. Sorry, that's a bit blurry. Okay. That is a function that sort of looks like this. Okay? So this is the future. This is the present, and this is the past. All right, and this is what the function does. Now there's a number that we can't represent. The number is this: the integral from minus infinity to infinity of e to the x squared dx. Here is the number. Now this number, right, makes no sense, because it's sort of the only way I can draw this number for you is it's the area underneath this curve. It's sort of the area here. All right? But it's not exactly that area. All right? So we don't die. Okay? So what happens is, you'll see it in here, and I'll show you. We're nothing more than quantum mechanics. That's right. It's exactly right. How close you were to the universe, my friend. So, this equation, right, this thing here, if you look, it's got it here. Look, e to the minus mw x squared over that. So see that? E to the x squared? It's right there. That's the number. Universal waveform function. Sort of. It's more, it's one type of wave function. It's one frozen in time. And it's only one dimension at the moment. Why not exactly that area? That's what no one has been able to figure out. No one has been able to figure out mathematically why that happens, and we don't even know the number. It's the only way you can describe it is an infinite sum of other numbers, right? So it's like 1 plus a half of a half plus a half of a half plus a half, and you've got to go for infinity. That's not actually the equation, right? It's something like that, and it goes for infinity, and that is the only way. So if there's no time, if we lived outside of the universe, that number would exist. But inside this universe, because we are only four-dimensional, there is no way to represent that number without having an infinite amount of time. Yeah. And so where that number pops up is in quantum mechanics, and it pops up right here, right? It pops up right here. Here are all the rocks that everyone's been throwing, right? So Cyanide, Homie, Fransman, McDuda, you know, everyone here is throwing rocks, Nelly Bell, right? And you would think that all the rocks should land here. But sometimes one of you throws a rock and the rock just disappears. No one knows where it is. And then someone finds it on the other side of the world. It's the weirdest thing in the world. And what's funny is that it exactly maps that number that no one can figure out. Right, so the point is that number is not exactly 1, it is 84%, and the missing part no one can figure out, and that missing part is where the rocks go. Yeah, it could have, but they were standing on the same point. Exactly. And when you do that with quantum particles, that's exactly what, and no one knows why. Up until today, no one knows why. In fact, I did my physics degree because I'm hoping to try and figure out why, because no one else has been able to find it. Time doesn't exist. Time is something created by man based on arbitrary number and rotation. You are correct to a certain extent. Time is a spatial dimension, right? But it's still a physical dimension, right? Which means that you need an infinite amount of that dimension to represent that number, and we don't have it, right? So not in this universe anyway. Time is a construct of man's mind. Throw me, let's see what happens. Imagine that. McDuda's one of the particles that disappears. You call me, hey man, I'm in Iraq. I threw a rock and I'm in Iraq. That was a really bad joke. All right, so that's it, my friends. That's the question today. That's Gabversity. Mind equals blown. Well, remember, we're facts. Don't give a shit about your feelings. Absolute pleasure to see all of you. Until next time. All mass based on spinning. Sometimes. Always welcome, Samantha. Lovely to see you all. Well, Cyanide, it takes one to know one.